physics experimentalist, and this is the introduction to the theory of free-falling objects, why everything falls at the same rate, regardless of mass, composition, or different inertial frame of references, like Moon, Mars, Earth, and Jupiter. My inspiration came from Galileo, one of the greatest scientists who started the laws of motion. But the most important thing about the Galileo was he had to slow down the motions, not by free falling, by rolling on ramps or inclined plane, to find out that uniformly accelerated motion. And he discovered one of the most important things. And then he discovered that rolling objects on a ramp, they do not speed at the same rate, so it changes. So in other words, he discovered the distance they travel is equal to half of acceleration times time squared. And he also discovered that the velocity is equal to mass times time. So every second, or at that time, the clock was not even invented yet. So what Galileo did was so important. The reason why he could find out this uniformly accelerated motion, which is, let me write this down. Galileo's uniformly accelerated motion, which is half of acceleration times time squared. He also discovered velocity equal to acceleration times time. I also, inspired by Michael Faraday, one of the greatest experimentalists. He also did the same thing, but Michael Faraday did with light. So he had to polarize the light, passing through a brick, which was glass brick, and then he discovered the interaction of magnetic field on the light. And this was also a great discovery because he laid the foundation for Albert Einstein's general relativity, which means that any lights or the sun's light passing through the huge massive stars will be deflected or bent. Well, of course, I have to explain every one, and then I have some experiments who will substantiate my theories. And it is so important that what they did, they were exactly the same. I mean, Michael Faraday slowed the speed of light, and then Galileo, he did it for motion of the rolling balls. I had to replicate what Galileo did 400 years ago with ramp, pendulum, and free falling. And I also theorized the main factor for free falling objects, or balls rolling on an inclined plane, or ramps, or pendulums, are partially gravity, but mostly the mass in motion, and especially the gain kinetic energy. Well, of course, I had to substantiate my theories by many experiments, which I will demonstrate in a minute. I also theorized that Galileo's formula, which is half of acceleration times time squared, can be analogous to kinetic energy, which is translational kinetic energy, which is KE is equal to half mass times velocity squared. In many aspects, Well, I have to do some experiment I will display in a minute. So, half of acceleration times time squared is equal to ke half of mass and velocity squared. I have to explain how the ramp works. See, this is a horizontal plane, and as you can see, there's a steel ball, it's 110 grams, and a horizontal. You see, it's not moving at all. The reason why it's a horizontal. So this has exactly 110 grams, the mass is 110 grams, so it's pushing on Earth, and Earth is also pushing 110 grams on the opposite side, so they cancel each other. That's why it's not accelerating. But the important fact is, this is accelerating toward the center of the Earth at 9.81 meter per second squared. But when it's a ramp, it's entirely different. See, you can see I drew this, so you can see when it's the horizontal like that, there is no acceleration. But the ramp is different. When the angle changes, you see, this is what happened. And this is the weight. But you can see the weight is not canceling the support from it's not canceling the support from the ramp. The reason why they're not in a straight line. And you see there's an angle here. So the more angle I have, the more acceleration I get. So if you can see, this is what Galileo did. So this is the way the ramp works. So in other words, the ball is rolling toward the center of the Earth, but because this has to roll through the rate, that's why it's slowing down. So what Galileo did, I think he probably slowed down the acceleration to the gravity probably 10 times. So did I. So this is the reason why the ramp worked. So the ball rolls down, so the more incline you have, or the more the angle, the more acceleration you have. But this is the ramp I have. You see, this is exactly 10 meters, but I will explain exactly how that works. And I found this Galileo's ramp in a science book. I'm assuming this is almost the gravity is 1 meter per second squared. So this probably is 6 meter long, and you can see the acceleration to the gravity. Each successive seconds, it increases more and more. Well, of course, I have to explain Galileo was not the first one who did this. Almost 2,000 years ago, his name was John Philippus, and he dropped some balls and don't have no idea what they were. And what he did was not conclusive. He had no idea why the balls or different masses or different composition fall at the same place. But the most important one did before Galileo, his name was Simon Stevens. He was a Dutch physicist, and then he did it on this church called Delft in 1667. So what he did, he had some lead weights, different weights, so he dropped them, then he realized they fall at the same rate. But unfortunately also Simon Stevens' idea or experiment was not conclusive because he could not find out why they fall at the same rate. He didn't know. But Galileo found out, and then I will explain how he did it. This is the principle for Galileo's ramps, but I have to explain something. When Galileo did this experiment, and the clock had not been invented yet, and that was almost like 400 years ago, but he was so genius, he used his heartbeat, and he also used a water clock, and it fact, the water clock was invented 2,000 years ago by Stephanus, which was one of the great scientists at the time anyway. So what Galileo did, instead of time, because time was not even discovered at that time, he discovered after 1 notch or 1 second, the ball rolls 1 notch. After 2 seconds, he discovered 2 times 2 is 4, times half of acceleration is going to be 4. After 3 heartbeats or after 3 drops from the bottle, he discovered 3 times 3 is 9, and 9 times half of the acceleration, and so on. And after 4 seconds, he discovered 4 times 4 is 16, and 16 times half of the acceleration. And then I wasn't sure about that. Then I had to conduct my own experiment in the lab. And then I realized I had this 10-meter ramp, and it worked exactly the same. I also had, well, of course, this ramp I have to explain. The acceleration to the gravity is 1/20th of the Earth gravity. Is 50 centimeter per second square. And then I had to make another one, which was higher than this with more acceleration. That was 1 meter per second square. But unfortunately, my lab is so small, so I won't be able to display that one. But I will explain this one, the way it works. This is my ramp. As you can see, it's exactly 10 meters, but I have to go step by step. I will explain. See, the first second in my ramp, the ball rolls exactly 25 centimeters, which is half of the acceleration. And the height on my ramp is 39 centimeter, and the acceleration due to gravity is exactly 50 centimeters per second square. So it's almost 20 times less than the gravity of Earth. And as you can see, the first second, it travels half of the acceleration according to Galileo's formula. And then the second, and after 2 seconds is 2 times 2, which is 4, and 4 times 25 centimeters is exactly 1 meter. And you can see after 3 seconds, it's exactly 3 times 3 is 9, and 9 times 25 centimeters, half of the acceleration is 2.25 meter. And after 4 seconds, you can see here, after 4 seconds, 4 times 4 is 16, and 16 times half of the acceleration is exactly 4 meters. And after 5 seconds, you can see it's 6.25 meters, and after 6 seconds is exactly 9 meters, because 6 times 6 is 36, and 36 times half of the acceleration is exactly . This is the ramp I made, but it's different. This is a plastic ramp, and it's extremely sharp, and it works perfectly with the steel balls. Well, what I did was different from Galileo. So I had to bend from the center, so I could do very slow-moving pendulum. Why did I do this? Because I could monitor the acceleration and how far the balls travel. And as you can see, when I roll down this 36 grams and 72 grams, see, they roll back and forth. Well, of course, there's no doubt there's a friction, but you can see the 72 grams is propelling itself more, and the reason why is getting more kinetic energy. Well, of course, I have more experiment I will show in a second. See, after few seconds, they go out of synchronization because this 72 grams is gaining more energy and propel itself more. And as we can see, well, of course, I'm not going to do that. After a few minutes, the 36 grams will stop completely, but still that 72 grams is rolling back and forth due to the gain kinetic energy. I have two more ramps over here, or two inclined plane. See, this one, acceleration due to gravity is 50 centimeter square per square, but that one is 1 meter second square. So we can see how fast they move. See, this one has more acceleration, even though the Earth's gravity is not changing, but this one has more velocity. So it's exactly 1 meter. It takes 1 second here and also 1 second up. 1 second, 1 second. But this one, each one or each half takes exactly 2 seconds. So you can see the difference. See how fast that one moves. First of all, I have to explain these posters, and then I'm going to demonstrate each one. This was the ramp I showed a few minutes ago, and this is exactly 10 meters. And as you can see, the height from the floor is 39 centimeters. But there's something important here. After 1 second, and the ball, or the still ball, travels exactly 25 centimeters. But as you can see, the acceleration due to gravity on this one is 50 centimeters per second square. So half of the acceleration is 25. But after 2 seconds, 2 times 2 is 4, and 4 times half of the acceleration is exactly 1 meter. And after 3 seconds is 3 times 3 is 9, and 9 times half of the acceleration is exactly 2.25. And after 4 seconds, 4 times 4 is 16, and 16 times 25 centimeters is exactly 4 meters. And after 5 seconds is 5 times 5, 25, and 25 times 25 centimeters, 6.25 meters, and after 6 seconds is exactly 9 meters, so 6 times 6, 36 times. But see, as you compare, here the acceleration is exactly double. Well, of course, I can't display that because my lab is too small. And this one, the acceleration due to gravity is 1 meter per second. So you can compare, see, the proportionality is not changed. This one has more acceleration, so the still balls are rolling more. But as you compare, the proportionality is exactly the same. Because the acceleration due to gravity on this ramp is exactly 1 meter per second. As you can see, the first second the ball travels, or the still ball travels, exactly 50 centimeters. But after 2 seconds, 2 times 2 is 4, and 4 times 50 is exactly 2 meters. After 3 seconds, so is 3 times 3 is 9, and 9 times 50 centimeters is exactly 4.5 meters. But after 4 seconds, 4 times 4 is 16, and 16 times 50 centimeters is 8 meters per second. So as you can see, the proportionality of increasing in position is exactly the same. Well, of course, these are the 2 ramps just displayed a few minutes ago, and this is the slowest I could get, and I could see a lot of things on this. And as you can see, this is 72 grams still ball, and that one is 36. And this one accelerated extremely slow. This is almost a 1/20th of acceleration due to gravity on Earth, and that one is exactly 1/10 of acceleration due to gravity. So each part, or each, is 1 meter here, 1 meter there. So each part ball travels exactly 1 second here, then goes up 1 second and comes back. But why did I do this? Why did I bend this from the just wanted to monitor the velocity and the acceleration. As you can see, both of them are graduated with centimeters, and I can precisely see where the ball's location is and can tell how far do they travel. As I mentioned, I theorized that the free-falling objects or balls rolling on the ramp or on pendulum is partially gravity, but mostly is their motion, mass in motion, and gain kinetic energy. And this substantiates my theory. What I did, we have double ramp, which I showed a few minutes ago. It was the black ramp, and as you can see, it has two rails, and the acceleration to the gravity is exactly 50 centimeters per square. Yeah. So it takes exactly 2 seconds from the start to the finish point or the center line, and I had to choose half a mass, which is 36 grams and 72 grams, and then roll them down simultaneously. And then what I saw, after few periods back and forth, they went out of synchronization, or they went out of phase. The reason why they did this, because 72 grams, once it gets here, because of the mass, it gains more kinetic energy and propels itself more. But 36 has the same velocity. I mean, they're exactly the same velocity. But what it does, 36 gains less kinetic energy, so that's why they go out of phase. Now, this is so important that I have to explain. This is called Hamiltonian Mechanics. It's one of the most or very impressive in mechanics. And Hamiltonian Mechanics says that, when it's a moving ball in a pendulum, of course, or the ramp, is the sum of the potential and kinetic energy. And he was an English scientist, very famous for this Hamiltonian Mechanics. So as you can see, we have free-falling balls or steel balls. We have ramps like me, the one I have, and then we also have pendulum. As you can see, in all three cases is the Hamiltonian mechanic. So it means that conversion of gravitational potential energy to kinetic energy, and the kinetic energy to gravitational potential energy, back and forth, back and forth. And this is the same way. As we can see, if the ball here on top, let's say 40 meters, has exactly 40 joules, and then it has exact kinetic energy 0 joules. By the time it gets to 20 meters, see, potential is half, but the kinetic is also half. But here's exactly the reverse. Kinetic energy is what? 40 joules, but the potential is 0. So is it pendulum. As you can see, when the pendulum rolls back and forth or swings back and forth, when it comes here and then go back, it's exactly one period. But something important happens here I have to explain later. This is called the second laws of thermodynamics. So every time this ball rolls back and forth, or it doesn't matter, or even free falls, or even the pendulum, something important happens. It does the work, and then it's pushing air, so the periods are getting smaller and smaller.